welcome to the Ponderings podcast. This is your host, Milo, and in this episode, I'm going to be talking about quantum mechanics, giving a brief history of old quantum theory and then new quantum theory, and then at the end, I'll be talking about a little bit on decoherence, and for the next episode, I'll be sort of comparing quantum decoherence with Whitehead's negative prehensions. This will be the first episode of the SpookyCast. I'm thinking for October I'm going to be making some sort of series centered mainly around quantum mechanics because it's pretty spooky and eerie. Very strange. That's sort of the plan. Alright, so for this first episode, I'm going to get started giving a brief introduction. Quantum mechanics and quantum physics are interchangeable terms. It's just basically referring to the nature and the matter of the smallest particles in the universe. So atoms, protons, electrons, and quarks. I'm going to be talking about their weird behavior that can't exactly be quantified. And you have to use probability to guess the nature of the behavior, and that's why it's very weird or it's hard to understand. We don't have a precise way to tell the exact position of these particles and if we do have the exact position of these particles, we can't tell their speed. I'll explain that more later, but they're just weird. Basically, I just wanted to mention that when things are investigated at this quantum level, they seem counterintuitive to the laws of physics. So I'll get started on the old theory of quantum mechanics. This will be talking about Max Planck and black body radiation. So black body radiation, it's when things heat up. So we infer that energy must increase as the frequency increases. So, when things heat up, they change color from red to orange to white and then to blue. So the law of conservation of energy states that light would keep climbing that color ladder the hotter something gets. So what Max Planck realized is that what he termed a black body radiation, there's this thing called ultraviolet catastrophe. It's the light wavelength at the quantum level. It actually jumps from place to place rather than continuously increasing. So we would think that the wavelength frequency, as it increases, that the energy would increase continuously. So sort of like a ladder. But what he figured out, Max Planck, is that the light actually jumps from place to place. So instead of increasing in energy as the frequency increases, it distributes less energy into shorter wavelengths, jumping from one wavelength to another. And so this would be called Planck's constant number, and this number is used to sort of quantify or measure the pockets of energy as it increases, or the space where they're jumping to. Yeah, okay, so it's just stick with me. So that's sort of the old theory of quantum mechanics, and we're still going to be talking about that, and then I'll mention when we sort of get into the new theory. But yeah, this is sort of where it's starting to get weird. Planck discovers this. They're jumping. The behavior's not continuous. It's sort of weird. But okay, so I'll get into particle versus wave physics. So James Clerk Maxwell's light experiment in the 19th century. He said that light waves work like ripples. That's how we sort of understand it. If there are two different ripples next to each other, when they meet, they will cancel each other out. So light moves sort of like a wave. And then Einstein, in his photoelectric effect, said that light is composed of tiny particles, photons, which behave like waves. So here's where it's like the particle versus wave controversy, because it's like, how can these particles also be waves at the same time? And it all depended on how the observer was measuring these photons in the experiment. So one thing that's really important to think about is that in all of science, the observer you can't abstract the observer from the experiment. You can't abstract the paradigm or the theories from affecting the results or the outcomes, because the observer will always sort of have their own, not just biases, but their own paradigm, their own theory behind it. The variables will be having to do with that theory. Of course, usually when scientists are trying to experiment on things, they're trying to disprove their hypothesis or their theories, or that would be the right way to do it. But again, it's still centered around a sort of paradigm. Again, particle versus wave physics exemplifies that the observer affects the outcome or what happens, because the observer is a part of that interaction or relationship. So there's the photon's wave-like movement, and in this movement, they had an experiment where there was a cardboard box with a small hole drilled in the box, and if you shine a light through it, the light will pass through the hole and spread out like a wave. And according to classical physics, the single photon, the light particle, would travel through the slit to the opposite side of the hole. So that's sort of like just common knowledge of what we think would happen, right? But actually, the photon moves in a random direction every time, like the single particle. If we're looking at just like a light beam, it would create that sort of like, it'll pass like a wave. It'll like have the same pattern every time. But if we're looking at the particular photon, it moves in a random direction, and if you let those photons pass one at a time, the random locations would start to look like the pattern of a wave. So what we see on like a macro level is just the light wave. But when we're looking at a photon, there's actually a lot weirder movement happening. It's a lot more random. So Einstein discovered that these photons always fall into discrete units of energy. This would be called, again, the black bodies of Planck's observation, the Planck's constant, the number he calculated for the jumps in light waves. So those jumps, they land on sort of these discrete units of energy. And each photon acted like a drop in an ocean wave, which went with the wave but could also become a different drop of that wave each moment. So again, we could track the movement, but then the exact location is unpredictable. So let's talk about the Bohr model, the atom model that we usually see in textbooks and things like that. It's the picture of an atom with its photons, electrons, and neutrons, and they sort of create an orbit around the nucleus of the atom. They're usually in discrete positions, leaping from one position to another. They skip the space in between. For Planck's constant, he counts for the locations that the electrons were allowed to orbit, following the same patterns as photons, blackbody radiation. Electrons happen at specific positions with no space in between. So again, just think about the textbook sort of atom model. You have your nucleus with the neutrons and the photons, and then you have the electrons going around it. So in the new theory of quantum mechanics, the model's going to be different, and there's going to be more uncertainty about the movements of these particles. And there's also more particles than we thought there were. We thought that it was just electrons and protons and neutrons, but actually the electrons and the protons can be divided into even smaller particles called quarks. And these quarks, they actually appear and disappear in die and, become in a very, very rapid and random fashion, and there's also very different names for them and all that. I'm still learning all this stuff. Honestly, I'm learning all these things on my own, and it's really to help me understand Whitehead's philosophy more, because he was a mathematician and studied the philosophy of physics and all these things. Alright, so yeah, electrons move like waves similar to light. Matter, atoms, and its components move in crazy and unpredictable ways. The tiny bits resemble a wave pattern. But if you're looking at an individual quanta, electron or photon, their movements are unpredictable and bizarre. And quantum mechanics shows that the universe does not make sense. Right? Here we have an example. If you imagine a glitch in a video game, there's a house that you can't enter at first, but somehow you're able to enter, but when you enter, the stuff in the house doesn't make sense, like it's empty or something. Like the programmer has not finished programming. That's sort of what it's like when observers, scientists, start observing the movements and what goes on in the quantum level of reality. Like it doesn't make sense. It's like a glitch in a video game. So we have to think of quantum like that. It's not going to make any sense in our normal classical view of physics or how laws of nature are supposed to work. Alright, so the Heisenberg Schrodinger model of the atom, it's going to be different from Bohr's model of the atom in that each electron acts as a wave or cloud around the nucleus. So there's an orbit, but in this case it's called an orbital rather than an orbit, because the electrons sort of act like a wave function. They have very different shapes, like spheres, dumbbells, daisies, very, very weird shapes in how they sort of move around. So it's sort of like it's a wave or a cloud. So an electron cloud. I think when I was learning science in middle school, they talked about this, but all I remember is just the normal like Bohr atom, where it's like just you got the nucleus, you got the protons, neutrons, and electrons. Or maybe I wasn't paying attention enough. I don't know. But apparently this is sort of the current model of the atom, as far as I know. It's not, the electrons don't orbit the atom, it's more of an orbital. They have very weird wave functions going on. So Heisenberg's major contribution is the uncertainty principle. He basically found out that if the speed of an electron is known, the position is uncertain, and vice versa. So it applies also to everyday size objects like a baseball. If the baseball speed is known, then the max precision of its position is less known, and vice versa. So if we know the position, we can't know the speed. But if we know the speed, then we can't know the position. And that's sort of what it's like when scientists are trying to figure out the exact location or predict the route of an electron or a photon. They can, if they pinpoint an exact location, they can't pinpoint the exact speed. They would have to have a probability for that. Same thing, they could figure out the speed, but if they figure out the speed, then they can't figure out an exact location. Movement is weird, right? So quantum wave functions of two states must be coherent to interfere. So measurement destroys quantum coherence. So in this case, it's like the particle versus wave. If it depends on how we're observing it. In one way of observing the photons or electrons, we'll see particles. In another way of conducting the experiment, of observing it, we'll see waves. So measurement destroys quantum coherence. What this means is that us as observers, we're not specifically destroying something. We're just affecting it, So, better said, measurement affects quantum coherence. How we're able to understand or make sense of the quantum world. The observer is part of the quantum system. Quantum decoherence must be understood in relation to its situated environment. Again, so in order to understand things like coherence or decoherence or just what's going on, we also have to realize that the observer is involved, how the experiment is laid out is involved, the paradigm which the scientists are sort of looking at the experiment and conducting the experiment, their point of view, the theories behind how they constructed their experiment or what they're trying to prove or disprove. All of these things are going to affect what the quantum world ends up doing or how we end up perceiving it. Which, again, it's like the scientists we can't extract ourselves from the experiment or the measurement, because the observer plays a part. The universe sits somewhere. It's surrounded by other stuff and interacts with it. We can't... It's like going back to embodied cognitive science or just like the embodied mind. Like the quantum world is embodied in that it is somewhere. It's a being in a world. Not necessarily the particles, but just like it's in the world. It's situated in a world. It's situated in a lab. It's situated in a certain way where the observer is measuring it in a certain way, so a certain outcome or possible outcomes are going to happen. Basically, the observer is important and it plays a part in how the measurement affects the outcome of these things. Anyways, superposition. This one is kind of weird, and the next couple of slides I'm probably going to have a hard time explaining these things. I'm still figuring it out, but it's the feature of a quantum system whereby it exists in several separate quantum states at the same time. Quantum superpositions occur when a particle that is in superposition interacts with another particle. The two become linked into a composite superposition. Back to what I said earlier, these quantum wave functions of two states must be coherent to interfere. I can sort of get into Whitehead, where it's like the actual entities, they have to be relevant to each other for them to sort of prehend each other or not prehend. And when actual entities are prehending another entity, a positive prehension, they're sort of seizing that data into their own being, into their own constitution. And if they're not positively prehending, which would be negative prehension, it's not coming into their being or their constitution. It's not coming into their subjective unity of experience, but instead it's another relationship of separation, or even a negative prehension is a relationship. So even decoherence in quantum mechanics all of these things are relationships. The observer, the quantum, whether things are coherent and relevant, or whether things are not relevant, everything is relationships, or everything occurs in the form of relationships, even in the quantum world. So I'm going to talk about quantum entanglement. So quantum entanglement is a superposed state of two particles whose interaction has turned them into a single quantum entity. System and environment merge into a single superposition. The initial quantum systems become more and more enmeshed or entangled with the environment as time passes. So this is what I mean when I say quantum kind of goes all the way up. it starts with superpositions, which are, in quantum mechanics, coherent. And because the superposition is in the original quantum system, or because the superposition in the original quantum system is entangled with the environment, we can no longer see or observe the superposition just by looking at the little part of it. So, there's no loss of superposition. We only lose our ability to detect it. So there's a lot of weird stuff going on. When two particles become enmeshed, or when they interact and turn into a single quantum entity, they're in a superposition. It's sort of how we see the world now. We're not able to detect these superpositions. We lose our ability to detect it because they're entangled. It's an entangled environment. Back to the Heisenberg and Schrodinger model of the atom. So the electrons and photons, they can actually be divided into quarks, and these quarks can't be only like single particles on their own. They have to be a part of a whole. They only exist as part of an electron or part of a proton. And that sort of is how, sort of how the entirety of existence is built up. Like, these parts are always part of a whole. Like, the electrons and protons and neutrons are part of an atom, and then atoms are part of molecules, and molecules are part of organisms or cells, or, so on and so forth. So, what is decoherence? An isolated particle can exist in a superposition of states, like not having a defined orientation of spin until the spin is measured. So measurement is what determines the location. This is not exactly defining decoherence. So decoherence would be the superposed states' ability to interfere with each other. So in the double slit experiment, the photon particles would act as a wave or as a singular particle depending on how they were being observed. Again, observation is very important. Either way, the pattern, whether particle or wave, would create an interference pattern. How we're observing affects how these particles interfere. How we're measuring affects these particles and their patterns. So in simpler words, information is lost due to entanglement with the environment. Decoherence has to do with this entanglement with the environment. It's, again, negative prehension. It's a relationship where information is lost or rejected. Decoherence has exactly to do with our lack of ability to be able to detect all of the information in the universe. There's information that is lost when measurement, observation, entanglement occurs. I know that superposition is usually explained as like there's, imagine if there's like another you in like a different parallel universe or something. That would be a superposition, and it can't exist in this world because it's not coherent. It doesn't make sense. So if you think about that sort of in the quantum realm, two particles could be in the same place at the same time. That would not make sense to us, but it's something that happens. And it happens because of this principle of decoherence. This decoherence doesn't allow us to be able to detect all these superpositions. Anyways, yeah, the quantum world is very weird. Very weird stuff going on. I hope that this introduction sort of helped. I just wanted to give kind of a brief introduction to sort of these different, that, black body radiation jumps from different pockets of energy as the light wavelength increases, that it's not a continuously increasing sort of thing. They're like jumping from place to place, and then, particle versus wave. that observation has a lot to do with how the things are affected or how the experiments turn out. So we can't subtract ourselves from our experiments, from science. We can't abstract ourselves from these processes. So yeah, it's very weird. But yeah, just keep in mind that there's weird things happening in the quantum level. These quarks, they always move together. They appear and disappear, but they have to be a part of a whole. And that sort of goes into the fact that you can't abstract things. You can figure out the exact location of something, but then everything else will become unpredictable. Or you can sort of figure out the speed of things, but then everything else is unpredictable. A lot to think about what all this would mean philosophically when we're just applying this quantum entanglement and all that, and observation and how paradigms affect how we see things. It's sort of like what I was talking in the last episode about active inference. We predict things because of the way we're built, because of our experiences. So we have a very specific view of things, and it's hard to get out of that view, that worldview, that paradigm. But yeah, this was part 1. Next week, I'm going to do part 2, gonna talk more about decoherence, explain that more, try to understand it with you, and I'll be comparing it to Alfred North Whitehead's theory of negative prehensions. Yeah, this is hard to understand. It's just weird. I think you gotta just accept it. It's like with Whitehead, it's like, I don't know what you're talking about, dude, but once you get more, once you get more exposed to his things, it sort of starts to make a little sense, or you just start to be more accustomed to the fact that things are gonna work out the way we think they are, I hope this was entertaining, at least. Yeah. See you next